In this video, we're going to learn about recursion. Recursion is essentially when a function calls itself. There's sort of this nesting where something is put inside of itself, maybe a smaller version of itself. This has spawned any number of ridiculous jokes on the internet. So recursion, in order to understand recursion, you must understand recursion, and so on, and so on, and so on. And then silly things like the most interesting man in the world here. And even XKCD comics, where the comic is nested inside of the comic itself, inside of the comic itself, inside of the comic itself. All right, but recursion is a really interesting and useful thing. It can be used to create all kinds of interesting fractal patterns or branching patterns, which is what one of the assignments you're going to have is going to do. Things like this as well, right? Where things are repeating themselves, but perhaps smaller, right? There's this same triangular shape repeated many, many times over. Now, a lot of people mix up recursion and inception because of the Inception movie. But these are actually not at all the same thing. Inception, if you recall from the movie, is about planting an idea in somebody's head, but they do it with dreams within dreams. And that's the recursive part that people are mixing up. There's this, something is happening inside of something else, and that is recursion. Okay, so let's go look at some code finally. So here I have a Fibonacci function. Actually, I've got some comments from when I was test running this video. I'm going to get rid of those for now. All right, so I've got this Fibonacci function. Now, if you don't recall what the Fibonacci sequence is, it's a sequence of numbers that usually starts with 1 and 1. And then you get each additional number by adding up the previous two. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, 21 plus 30, you get the idea. I have a little loop here. I am going to print out the first 5 Fibonacci numbers. And so let's take a look at that. All right, so my first 5 Fibonacci numbers, 1, 1, 2, 3, and 5. That matches what I have here, 1, 1, 2, 3, 5. Let's go out to 8 and make sure I'm correct here. So I'm going to print out the first 8 Fibonacci numbers. All right, so I've got 1, 1, 2, 3, 5, 8, 13, 21. That matches with what I put here. This seems to be working. Great. Let's get rid of this window so we can see more of the screen. Oh, you're seeing some of what I'm going to do later. Okay, so let's see how this works. Well, it's got the recursive feature where the function calls itself inside of its own body of code. That's kind of interesting. That's the recursive aspect of this. So I have an if statement that says if n is less than or equal to 0, I'm going to return a. I'm going to return the first input to my Fibonacci function. Otherwise, I'm going to return whatever the result is of calling the Fibonacci function. But I'm going to modify the arguments a little bit. Okay, so let's go through an example run of this. So I pass in 1 and 1. Those are my first 2 values in my Fibonacci sequence. So I could change those if I wanted to. And then I pass in I. And I is my sort of countdown to when I'm finished. So I is going to be the n right here. And each time the Fibonacci function calls itself, n gets decreased by 1. That's the way in which it's a countdown. So let's look at an example of what actually is getting passed to the function. So I'm going to have a column for my A, for my B, and for my N. And my A starts off as 1. That's what I pass in. My B starts off as 1. And my N starts off as... Actually, let's just worry about the 8th N. So I'll put in 8 for N. Now, 8 is greater than 0, so we don't go here. We go to the else statement, and then we call the Fibonacci function. Let's see what happens. Well, the first argument, the first A, becomes the B, or the B becomes the A, rather. So I put a 1 here, and that's actually this 1. And then the B becomes the sum of the A and B. So now that's not 1, it's 2. N gets decreased by 1, so I go down to 7 here. Next time we go through, 7 is still greater than 0, so we go to our else, and we call the Fibonacci function. Okay, so the B value is going to be this value right here. I'm going to put that as my new A value. So that's a 2. And then I'm going to add up A and B for my new B. 2 plus 1, these values, 2 plus 1 is 3. N gets decreased by 1, and this becomes 6. I go through again. I put my B value as my A value. I add up my A and B values. I get a 5 there. I decrease N by 1. I get a 5. I go through again. I put my B value as my new A value. I add up my two previous A and B values and get an 8. I decrease N by 1. And hopefully you see what's happening here. 1, 1, 2, 3, 5. I'm getting my Fibonacci sequence as my A values. And this can be kind of a difficult thing to wrap your head around at first glance. But what we're doing essentially with this change of arguments is we're decreasing down, we're counting down until we're done, and we're performing the Fibonacci operation where we add the two previous numbers right here. We sort of slide to the left one by moving this B over and figure out what our new next value needs to be by adding the previous two. Now, the other important thing about recursive functions, all recursive functions have this property. There is something called, there's at least one base case and at least one recursive case. And the base case refers to when we're stopping. And the recursive case refers to when we recurse or call ourself. So whatever function we're in, that function is going to call itself. Now there might be more than one base case. There might be more than one recursive case. This is a nice simple starting example because there's only one of each. It's really important to have a base case where you stop. Otherwise you'll get into something similar to an infinite loop, but with recursion, where you'll never end. Now let's move on to a turtle example. So I mentioned all those fractals you can draw, and one of the projects is to draw a fractal. So let's just go look at not a fractal example necessarily, but an example of what you can do with recursion with turtles. So I've got my recursive drawing function right here. You'll see that it calls itself. And I just mentioned how there's base cases and recursive cases. This is a recursive case. And I said you always have to have both, and there's no base case. So what's the deal? Did I lie? Why is there nothing down here? Well, in this situation, the base case is actually do nothing, right? That will make this function stop by not calling itself again. All right, so let's look at what I'm doing here. So I create a turtle. I call this recursive drawing function. It's gonna repeat, it's gonna call itself 10 times, and then it's gonna be done. So here's the turtle, here's the countdown. I check if the countdown is greater than 0. This is very similar to the Fibonacci example. It's not always as similar. It's not always just n greater than 0, but it's a very common way to do it. I'm going to set the turtle's color, its pen size. I'm going to turn it right a certain amount based on this countdown. Based on this countdown. That's an important aspect that helps you create these fractals, these smaller structures within, because the countdown is getting smaller. I'm going to turn forward, or I'm going to move forward. And then I'm going to recurse. I'm going to call myself again, this function. So let's run it and see what this does. Okay, so I create this wacky pattern right here. And a few things happen, lots of things happen. My color gets closer and closer to black as I go. My turning angle gets shallower and shallower. At first I'm turning a very large amount, tight turns, and then toward the end, I'm just kind of gradually, lazily turning to the right. I move further at the start, and I decrease how far this turtle is moving forward as I go on. And then the pen size, the width of this line, also decreases as I go forward. And that's all dependent on this countdown. So you can draw lots of interesting shapes with recursion, and this is just one simple example. So when you think of recursion, I want you to think two things. I want you to think of functions calling themselves and some sort of nesting. Recursion is not unlike, let's actually create an example here. It's not unlike when I call functions inside of other functions. So for example, I could print the sum of the list that I get from a range that goes from 0 to 5. Right? This is not recursion because it's not the same function calling themselves, but it's a nesting. Let's make sure this works. 10. Is 10 the sum of all the numbers from 0 to not 5? Remember, we're actually going up to 4. Range goes up to 1 less. So 1 plus 2 plus 3 plus 4. That sure looks like 10 to me. So I want you to think of nesting. I want you to think of a function calling itself. And then lastly, when you're writing your own recursive functions, you need to think about your base case and your recursive case. What is the thing that's going to repeat, and how is it going to get closer to stopping?